Hello everyone and welcome to this lecture. In this lecture, we will start a new topic and this topic is about signed graphs. So what are signed graphs? Okay. Till now we have seen the graphs where edges have plus one or just one weight, right? So weight of all the edges. If you see the adjacency matrix, we were putting one whenever ijth entry or vertex I and j have an edge between them. So we were putting one. In the sign graph now, edges can have in fact minus one weight. So adjacency matrix is now signed adjacency matrix. Some of the edges can have plus weight, some of the edges can have minus weight. Okay, minus means here for simplicity -1, plus means for simplicity +1. Okay, and actually, what is the motivation? Especially, actually, these graphs are coming out of some social forms. Okay, so suppose you see, let's suppose there are three people ABC, three people ABC. Okay, suppose A is friend with B, and let's suppose I denote this friendship by plus or +1. Okay, and A is also friend with C. Okay, it's more likely that in future B and C will also be friend. Okay, so friend of my friend is my friend. Okay, so sorry, friend of my friend, yeah, friend of my friend is my friend. Okay, very good. So such configuration, social scientists call, oh, this configuration is balanced. Okay, similarly, enemy of my enemy is my friend. Okay, so this is also, I mean, kind of natural. Okay, so suppose this. So suppose A is enemy with B, A is also enemy with C. It's most likely that B and C will become friend in near future. Okay, so this is also balanced. Okay, other things are actually unbalanced. Other things are according to social scientists. So like if you put these things, suppose A, B, C, A, B and C, and suppose this is all negative here. So I mean, there might be a case, there might be in near future that either B or C, B and C can be friend, A and C can be friend, and A and B can be. So this is actually unstable or unbalanced. This is unbalanced. Okay, unbalanced. And similarly, wherever there is just one negative sign, this is also unbalanced. So suppose, let's suppose this. So this is also unbalanced. It might be possible that in near future A and B will become friends. Okay, so this is also unbalanced. Okay, so actually the summary here is, if in a triangle or in a three people, okay, if there is just if there are even number of negative edges, we will call it balanced. So if you see that, so there are 0 negative edges, there are 2 negative edges. So if there are even number of negative edges, we will call them balanced and otherwise unbalanced. And this concept of balance and unbalance in C3 or a cycle on three vertices is generalized to bigger cycles. So suppose now you have a bigger cycle. Suppose let us take this one. Okay, let us take this one. Okay, and then suppose I put here plus and somewhere minus this. So there are even number of negative edges. So this is also known as balanced cycle. Okay, balanced, and suppose there are some other configuration where there are suppose odd number of negative edges. Suppose this. Okay, and these are plus. Okay, so this is unbalanced. This is unbalanced. Now from cycle, we actually generalize this concept to graphs. Now here comes the sign graphs. Okay, sign graphs are graphs. We have already told that sign graphs are the graphs where the edges can have negative edges and plus edges also. Okay, so in sign graph there are plus edges and minus edges. So what are balanced signed graphs? Okay, so balanced signed graphs. Okay, balanced and a signed graph where every cycle is balanced, where every cycle is balanced. Okay, and similarly we define unbalanced sign graph. Okay, now next thing is unbalanced sign graph. So these are sign graphs which are not balanced. Okay, so unbalanced signed graph. Okay, so these are the sign graph. A signed graph which is not a balanced sign graph. This is not a balanced signed graph. Okay, Okay, so let us see some more examples on balanced sine graph, and then we will see a very nice theorem on it. Okay, so balanced sine graph. Okay, so let us take one example here. If you see this graph, let me quick. Okay, now I will actually represent the negative edges by dot dot dot. So dot dot dot. So these are the negative edges, and the darker edges are actually the positive one. Okay, so this one, and let me go to one. So this graph, if you see that every cycle in it has an even number of negative edges. So this is a balanced sine graph. Okay, so let me quick one unbalanced sine graph. Okay, so unbalanced sine graph. Okay, unbalanced sine graph. So maybe I can cook this. Yeah. So there is just, I mean, I have just added one unbalanced cycle, so it will become unbalanced sine graph, and rest of the things maybe I can keep as it is. Okay. So this. Okay. So this is unbalanced sine graph. Okay. Now let us see some nice theorem related to the structure of balanced sine graph. If you see before writing that theorem, so let us see if you see carefully this balanced sine graph structure here, you see there are actually two chunks. So one chunk is this, one chunk is this. Every edge inside that chunk is positive edge, and between these two chunks, right, or between these two subsets, the edges are negative. Okay, and this is actually if and only if condition, that if such possibility is there, the graph will be balanced, and if the graph is balanced, then we will have such a structure. Okay, very good. So let me write the theorem. The theorem. Okay. Let GS be a signed graph, be a signed graph. Okay. Then GS is, or maybe with this. Okay. GS is then GS is a balanced signed graph. Is a balanced signed graph of if and only if and only if the vertex set of of GS, again I'm writing GS, can be partitioned into two subsets, into two disjoint vertex subsets. Okay, let us call S1 and S2, such that all the edges inside S1 are positive. All the edges inside S2 are positive, and and what, all the edges between S1 and S2 are negative, and all the edges between S1 and S2 are negative. So one direction is super easy, and another one is also not very difficult. So let us go to the proof of it. Okay, proof. Okay. So suppose there are such partitions. Suppose the first direction is, suppose there are such partitions. Suppose S1 and S2, such that everything here plus everything. So let me put some dark edge here. Okay, so on. Okay, and everything in between is negative. Okay. So you see that every cycle here. Okay, cycle means, so every cycle inside this is positive because there are darker edges or positive edges. Every cycle inside S2 is positive, darker edge again. Now let us consider cycle which is actually crossing S1 and S2, right? So if it is suppose you start at S1, it will go to S2, then come back to S1, right? And by doing so, it is actually covering even number of negative edges. So every cycle here is having even number of negative edges. So this is, so every cycle here, cycle has negative edges, negative number of, oh sorry, even number of negative. I'm actually have even number of negative edges. Very, very good. Very, very simple the case. Now let us take the opposite one. Okay, suppose the every cycle has even number of negative. Basically, every cycle is balanced, right? Then how can we have such partition? Okay. Now assume that let GS be a balanced signed graph. Balanced signed graph. So how can we actually prove this case? Okay. We will prove using a construction. Okay, we will prove using a construction. So suppose U and V is having a negative edge. So U and V are some vertices which is having a negative edge. Okay, so what you do, all the neighbors of U which are with which U is having a positive edge. Okay, you put all these vertices in set S1. Okay, so suppose, so all these are the neighbors of U. Okay, you put all these vertices in actually S1. So this is S1. Okay, and this U is also there. Okay, and all the vertices with which we have the positive edges. Okay, you put them in S2. Okay, so suppose this is S2 here. So this is S2, right? Okay. Now do what? Now do what? You pick any vertex here. You pick any vertex here. Okay. So suppose this is U dash. Okay. All the positive, basically the vertices or which are all the vertices which are having positive edge with U dash. Okay. You put in as S1 again. Okay. In this way you keep it, and all the negatives you will put in S2. Okay, you put in S2. Okay, very good. So suppose this is a vertex. Okay, and similarly do the all the positive ones for suppose this is V dash, you put here only. All the negative ones you will put here only. Okay, now what? Now since every cycle is balanced here, such configuration cannot be there. So suppose this is U dash. Okay, and then there is a positive edge. Okay, and suppose this is maybe V here, and these two are negative, right? Because this is so this positive edges cannot go out of U dash. So all the edges here are actually negative due to the fact that all the cycles are actually balanced one. Okay, very good. So this proves that in this way we can actually come up with two disjoint vertex subset, that all the edges inside any subsets are plus, and between any two subsets there are negative edges. Okay, there are only two subsets, by the way. So all the edges between these two subsets are negative. Okay, very, very good. So this is nice partition characterization of balanced sign graph. Okay, now let us see spectral characterization. Okay, so let me write it here. Spectral characterization of balanced sign graph. In fact, a sign graph, just sign graph. Let me now write a very, very beautiful theorem. Okay, very, very, very good. Okay, so okay, so let me write the theorem. Okay, let GS be let be a signed graph. Okay, with sign adjacency matrix, with the corresponding sign adjacency, with the signed adjacency matrix, with the signed adjacency matrix. Okay, suppose AS, I will just simply say. Okay, then GS is balanced if and only if, very, very powerful. Okay, whenever this statement, if and only if, okay, the eigenvalues of AS and again I'm making and the adjacency matrix and the adjacency matrix A of the underlying unsigned version or unsigned graph G are the same. Okay, are the same. Basically, it means that there is a sine graph, okay, and the corresponding sine graph you take. Basically, wherever there are negative edges, you make them plus. Okay, so this will be an unsigned version of the sine graph. Okay, if these two graphs have the same eigenvalues of its adjacency matrix, in one case it will be sine adjacency matrix, then and only then the graph will be, the sine graph will be balanced one. Okay, so let us prove it. How to prove this beautiful claim? Okay, so prove. Okay, now assume that the sine adjacency, so we can write the sine adjacency matrix of your sine graph as this, right? So suppose there is suppose this graph is balanced, so we are assuming that the graph is balanced. Okay, then we will prove that the a and a s has the same eigenvalues. Okay, so as you can write as this, right? A1, A2, and suppose this is some n, right? So these are the actually saying the negative edges. So this is corresponding to these partitions. Suppose this is S1, this is S2, and these are the negative edges, right? These are the negative, and everything here is plus. Okay, so these dash dot actually are, they are corresponding to n. A1 is corresponding to this, A2 is corresponding to this. Okay, very good. Okay, now remember as is nothing but, a is nothing but, you take mod of this, right? You take mod of n. Okay, you take mod of, maybe this is n transpose here, this is A2. Okay, so this is the adjacent. So we have to prove that now, since the graph is balanced, A, S and A have the same eigenvalues. So let us suppose there is a vector. So suppose this xy is actually lambda xy. Okay, so these x and y are actually conform with the size of A1 and A2 respectively. Okay, so how we can write this? So let me actually write here. So let me actually write here again. So this is A1 n, then n transpose A2. Okay, then this is x and y. So this will be equal to lambda. Suppose lambda is the eigenvalue, x and y. Okay, so we will have two equations, right? So A1 x plus ny, this will be equal to lambda x, and similarly n transpose x plus A2 y will be equal to lambda times y. Okay, now if you see carefully, let us see, let us observe. Okay, if you pick this matrix, basically the signed version of basically unsigned version of this. So suppose this A1 mod okay, so this n and that's A2. Okay, you see it carefully that you can actually indeed write this as xy equal to lambda minus xy. So actually I am making a shortcut, but it's not very hard to see. Let me see why. Let us see why this is true. Okay, basically these two equations actually are giving these two equations. Okay, so but why? So if you see here, and so maybe I will write here, and is nothing but negative of it, right? It is nothing but negative of this. Okay, so you can actually replace it by this, and then the proof is very in front of you. Minus n transpose A2. Okay, so minus x, sorry, y here, y, then lambda, then minus x minus y. Now it is easier to see. So what we can do is this, right? So this is nothing but, if you see that a1x, a1, yeah, minus a1x, okay, then minus ny is giving you minus lambda 1. Yes, so this is actually coming from this first equation. You just replace my minus. Okay, and the another one is what? Another one is this minus n, in fact plus ntx. Okay, because this is right, plus a2y, this is lambda y. Okay, the same equation, the same thing. Okay, so from here we can actually conclude this. Okay, so basically it says that if this hold, this also hold, right? So lambda is eigenvalue. So both of these, and they are the n number of eigenvalues in both, right? So both are having the same spectra. So both are having the same eigenvalues, the same eigenvalues. Very good, very good. Now let us move to the converse part. Okay, so now we will assume that, okay, now assume that all the eigenvalues, so eigenvalues of as and a are the same, are the same. Okay, now we will prove that this gives what, if the eigenvalues are same, then this means that the graph is balanced. How to prove this? Now again the spectral theorem will come into picture. We will find the number of closed walks of length k. Okay, so remember, using the eigenvalues, so if you see that a to the power k summation over all k's, right? Okay, so this was giving what? This was giving, so it's basically infinite trace of this, right? Trace of a to the power k. Okay, summation over. So now let me write the summation. The trace of a was giving what? The closed walks of length k. Okay, and this was given by what? This was given by, this is nothing but summation of lambda I to the power k. Summation of lambda I to the power k. Okay, so I equal to 1 to n, right? For any k, for any k, closed walk, right? Very good. Now what about this trace of, if you see, trace of a to the power k now as, okay, this is nothing but, if you see carefully, in fact, for any weighted adjacency matrix or weighted matrix, a to the power k will give you what? The weighted closed walk of length k. Where weighted closed walk means the weighted means here the weights of the cycle, weights of each closed walk, and the weight of closed walk means the product of weights of edges on the cycle. Okay, so here if you see that the product can be either 1 or -1. If the walk is balanced, right, the product will be +1. If the walk is unbalanced, and the product will be negative, actually -1. So here walk, I mean, like similar to cycles, we are actually defining balanced walk and unbalanced walk. So if the walk has even number of negative edges, we will call it balanced closed walk, otherwise unbalanced one. Okay, so this actually gives the total number of balanced closed walks of length k, minus number of unbalanced walks of length k. Okay, because they are coming with negative signs, so this is actually very easy. Now we know that, but this is also given by due to spectral theorem, this is also given by the same quantity, right? Same quantity, lambda I to the power k, I equal to 1 to n. Now if you see that there is actually 1 to 1, there is because these two quantities are same, right? But every cycle here is a balanced. Every cycle in the unsigned version of graph is actually balanced, because every edge is positive. That means what? If you equate them here, so this is nothing but 0. This is because every cycle is balanced. There is a 1-to-1 corresponding between closed walk, but there is none of the closed walk in unsigned version is unbalanced, right? So this implies that the number of unbalanced walks is, so this implies the number of unbalanced closed walks is 0, big 0. This implies none of the cycle is, so every cycle is balanced. Every cycle cycle is balanced. Okay, hence GS is, and maybe I will write in the next page. Okay, so that means GS is balanced. Okay, very good. Okay, so we have seen a very nice spectral characterization of sine graph. So if the eigenvalues of the sine graph and its counter unsigned, I mean its underlying unsigned version is actually the eigenvalues are same, then this graph is bipartite, and only then it is the graph is balanced. Okay, very good. Okay, and with this I am stopping this lecture.